Yes.
Yes.
Okay, what about the screen? Is it clear?
Yes.
All right. So, section 1 and 2, I sent you yesterday the videos about section 1 and 2, and uh, so those are enough if you want to revision from the video. And then section 3, I will continue now today by screen sharing of the PowerPoint presentation. Normally, we study this presentation in the school time. Now I am going to explain again on this presentation, PowerPoint presentation. So this section 3 was about rotational dynamics. Remember, dynamic is explaining the thing which is about the cause of emotion. Dynamic, when we say the dynamic, the question is that how an motion starts, or how can you stop a motion. This dynamic is explaining this. So rotational dynamic is explaining how a rotation starts, what causes a rotation to start, or what causes a rotation to stop. uh, Now we will make comparison between the translational motion and rotational motion, because the rules are very similar in translational, the rules or laws in translational motion, and the rules and laws in rotational motion, they are very similar to each other. So that's why maybe we will make some similarities, and we will see some similarities between these two rules, and then we will keep those things in our mind for a long time. So in translational motion, remember in the 11th grade you studied about this. An object starts moving by a force. If the force acting on the object is equal to 0, we say that object will stay at rest if initially at rest, or object will continue moving with constant velocity if initially in motion. And this law is known as law of inertia. In fact, the first Newton's first law of motion. And in chapter 1, we also talk about this. It was like this: if the net force acting on a object is 0, object follows a straight line path. Object follows straight line path. And or if the object is initially at rest, object will stay at rest. It will not move. So this is known as law of inertia, and that property of the substance is called inertia. But in rotational motion, corresponding quantity is torque, because rotational analog of force is known as in rotational motion as torque. If the net torque acting on an object is 0, so tendency of the object is to stay at rest if initially at rest, or to rotate with constant angular speed if initially in rotation. So this property of the substance is known as moment of inertia. So in translational motion, we have inertia. Rotational analog of inertia is moment of inertia, which causes object, or which keeps an object in rotational motion if it is initially in motion, or which keeps an object at rest if it is initially at rest, which is moment of inertia. They are similar, but they are not the same thing. They are different things. Now I am going to explain the similarities and difference between the inertia and moment of inertia. So let's continue. So this is the table which explains the similarities and the difference between the inertia. First, inertia is about translational motion, but moment of inertia is defined in rotational motion. So inertia is defined as, in the 11th grade, the resistance of an object to accelerate. So object does not accelerate, object does not start moving, or object does not change direction of motion, or object does not want to slow down. So this property of the object or substance is called as inertia in translational motion. But in rotational motion, corresponding quantity is moment of inertia. So it is the resistance of an object to accelerate rotationally. This is called moment of inertia. Yani object does not want to rotate, object does not want to stop rotation, So this is called moment of inertia. If moment of inertia is big, it is hard to start rotating the object. If moment of inertia is small, it is easy to start rotating the object. Or if moment of inertia is big, it is hard to stop a object from rotation. If moment of inertia is small, it is easy to stop the rotation of an object. So they are very similar. Of course, they are uh, different quantities. So as I said, it is harder to start or stop motion of a truck than automobile because truck has a greater inertia. It is harder to start or stop the rotation of an object if the object has a greater moment of inertia. Inertia on an object is proportional to its mass, greater inertia. We say in translational motion, but the same moment of inertia of an object is also proportional to mass, but it is not all. But this is clear. If you increase the mass of an object, its moment of inertia increases. And if you check the moment of inertia equations, all are some constant mass multiplied by r squared, some constant mass multiplied by r squared. So as you see, moment of inertia is proportional to mass. Yani if you increase the mass of a system if you increase by adding some mass to an object, its moment inertia absolutely will increase. It is proportional. Moment of inertia of an object is proportional to its mass. But that is not all. Why? Because moment of inertia of an object also changes with where the axis of rotation is chosen. So for the same object, if you rotate object about different points, so moment of inertia could be different. So moment of inertia also depends on about which point this object is rotating. So this is explained by this sentence: distribution of mass. Distribution of mass of an object. If you make distribution of mass closer to axis of rotation, so moment of inertia gets smaller, it is easy to rotate. So if the distribution of mass, yani particles of the mass, parts of the object is farther from axis of rotation, so moment of inertia is greater. If parts of the mass is somehow made closer to the axis of rotation, moment of inertia is smaller. So this is the similarity between the inertia and moment inertia, also difference between inertia and moment of inertia. This table is important about rotational motion. And now I will continue with the definition of moment inertia. This is defined moment inertia in your book like this: the moment of inertia is a measure of object's resistance to change in its rotational motion about some axis. So this is the definition of moment of inertia. Its symbol is capital I, moment of inertia, and it is the rotational analog of mass. So in translational motion, we have mass. In rotational motion, we have moment of inertia. And its unit is kilogram times meter square. We are going to learn why is it like this when we see the equations. And we know that, as I said, farther the mass of the object is from axis of rotation, if you make object farther from axis of rotation, it is the more difficult it is to rotate the object, more difficult it is to stop the rotation. Why? Because greater the object's moment of inertia. And there are some equations, some shapes about we should remember their moment of inertia equations. First one is point mass about axis. What does point mass mean? If an object follows a circular path, like this one, this object, it follows a circular path. Yani if it is in circular motion, so if it is revolving on a uh, orbit, so then this object will have a moment of inertia mr squared. So let me give example. Earth revolving around the sun, following a circular path. Yes. Is it a point mass? Yes. In this case, so Earth around the sun will have a moment of inertia which is mr squared. Or moon around the Earth. So is it following a circular path? Yes. Its moment of inertia will be mr squared. Or a car following a circular track. So the car is following a circular track. Yes, its moment of inertia is mr squared. So whenever an object follows a circular track, its circular path, its moment inertia will be mr squared. Second one, tin hoop, a ring, a ring. Tin hoop means ring about symmetry axis. So this axis is known as symmetry axis because this every point of this ring is at the same distance from this point, symmetry axis. So if you rotate this ring about this axis, this axis of rotation, this tin hoop or ring will also have mr squared, same as this one, because you can think that this ring has billions of small particles like this one. So all they are following the circular path. For that reason, this and that have the same moment of inertia equation. But third one is different. You are going to rotate this ring, tiniop or ring, not about the center, about the diameter. So this is diameter line. So it's rotating like this. So this is completely different than that. So ring or tin hoop about the diameter is half of this one, 1 over 2 mr squared. So which one is easier, this one or that one? Of course, second one is easier to rotate because moment of inertia, smaller moment inertia, easier to rotate the object. Fourth one is a disk or cylinder. Cylinder and disk both have the same moment of inertia about symmetry axis. It's a kind of, yeah, disk generally called this one. In the in the examples, 1 over 2 mr squared is the moment of inertia. And solid sphere about diameter, for example, earth rotating about its own axis, solid sphere about diameter, a kind of solid sphere, earth rotating about its diameter. So 2 over 5 mr squared. Thin spherical shell about diameter. It's a kind of football, and inside is hollow sphere, sometimes called hollow sphere or thin spherical shell. So it is 2 over 3. As you see, 2 over 5, 2 over 3. This has a greater moment of inertia than that. Yani it is harder to rotate a hollow sphere compared to a solid sphere. Solid sphere is easy to rotate, but a thin spherical shell, or which is called as hollow sphere, is hard to rotate. These two examples, these two are given, but there is no questions about these two examples in your book. One of them is hold your pen from the midpoint and rotate about this midpoint. So its moment of inertia 1 over t ml squared. M is the mass of this rod, L is the length of this rod. Or if you rotate your pen about one edge, and so it is 1 over 3 ml squared, so which means this is harder compared to that one, even 4 times harder to rotate a pen about the end compared to a pen rotated about the midpoint. I mean, these tables are general. These equations are given in the questions, but I think 2013 or 14 they ask just once, what is the moment of inertia of this? So, but they are not so hard, especially these 4, 5, and 6. Not these two. So many times you read about them, and you will remember them in the exam. And now we will continue with uh, what causes and how object starts rotating. Of course, we know that in translational force, in translational motion, force causes object to start motion. Remember, if net force acting on object is equal to zero, object is in translational equilibrium. We studied this in section 2. If the net torque acting on the object is equal to zero, object is in rotational equilibrium, which means if there is rotational equilibrium, angular acceleration is zero. If there is translational equilibrium, linear acceleration is zero. What if the force acting object is not zero? Also, object gains acceleration, which is known as Newton's second law of motion. What if the net torque acting on an object is not zero? Object gains angular acceleration, so it is known as Newton's second law for rotation. Their equations are also very similar. This is the equation for Newton's second law for motion. F is equal to m times a. And for Newton's second law for rotation is net torque is equal to, instead of m, what is rotational analog of mass? Moment of inertia. What is rotational analog of translational acceleration? It is angular acceleration. What is rotational analog of force? Which is torque. Net torque acting on the object is equal to I times alpha. This equation tells you, if you want to start an object rotation and increase its angular speed, yani to give this object an acceleration, you should produce some torque on this object. How great is the torque? So object gains a greater acceleration, because I is constant for a specific object. If you don't change object's mass, if you don't change object's axis of rotation, I is constant. It's a scalar quantity. But if you increase momentum, if you increase the torque, so which means object will start accelerating with a greater acceleration. So according to this equation, torque net is equal to I times alpha. As I said, I is moment of inertia. It's a scalar quantity. It's just a number. Torque and alpha are directly proportional. If you produce more torque, objects rotate with a greater acceleration. If you less torque, objects start rotating with smaller angular acceleration. But their signs are same. If torque is positive, angular acceleration becomes positive. If torque is negative, angular acceleration becomes negative. If torque is zero, angular acceleration is zero, as I said, because I is scalar quantity, I is a constant. So this equation is the equation which is known as Newton's second law for rotation. Sometimes they are adding here, instead of alpha, equation for alpha, which is delta omega over delta t. Yani torque is equal to I delta omega over delta t. They asked this in ministry exam, not in this form. So they inserted here, instead of alpha, equivalent of alpha, which is delta omega over delta t, change in angular speed by time, which is the angular acceleration. Questions or problems in your book are not so hard in calculations. So for one example is about throwing a dart. So a student is tosses a dart using only a rotation of her forearm. This is the forearm. And accelerates the dart. So this dart is gaining acceleration in that, along this tangent to the circular path. The forearm and dart have a combined moment of inertia of 0.075 kilogram meter square. So this moment of inertia is given I, so you don't need to calculate moment of inertia here. And the length of the forearm is 0.26. This length is a kind of radius of this circular path. It is the radius of the circle, so R is 0.26. And the dart, if the dart has a tangential acceleration of 45 meters per second square just before it is released, right here, so and it has a tangential acceleration which is 45 meters per second square. So what is the net torque on the arm and the dart? We will calculate the torque. We know the relation between torque and angular acceleration, but given is not angular acceleration, which is tangential. That's why you should first find what angular acceleration is. It is equal to r times alpha. So AT is given as r is 0.26, AT is 245, alpha must be calculated first, so which is 173.1 radian per second squared. And after that, it's easy to calculate the torque, because I times alpha is torque. I is given as 0.075. So alpha we just calculated, so 173.1. This multiplication is almost 13 Newton meter. So 13 Newton meter torque is applied to this dart and the forearm just before this dart released. And one more question I will solve. This is very popular in ministry exam. This is one of the standard test prep question. There are some sample problems and practice problems, but this is pretty important. This is most asked in ministry exam. It says that a force of magnitude 2 Newton is tangentially applied to a disk of mass 5 kilogram and radius of 0.1 meter. What is the angular acceleration of the disk? So there is a disk. I forget to draw it. Here is a disk, and you apply this force tangent to the disk, which means this force produces a torque. Section 1, chapter 2. if you apply a force tangent to a disk, this force produces a torque, and we calculate that torque by equation: force times distance to axis of rotation, or force times lever arm or moment arm. So we will calculate this force torque first, but this torque will cause this disk to gain some angular acceleration. So if we know the I for this disk, so we can use this to definition of the torque, and we can calculate angular acceleration. These torques are equals. In fact, they are defining the same thing, but in two different ways. One of them is the cause of the torque. Second one is effect of the torque. Torque causes acceleration. Evet, bakın burada şöyle bir zincir var. Force causes torque. Torque causes acceleration. Size acceleration soruyor. Ne yapacaksın o zaman? You are going to say that Ft and I alpha are equal. They are defining the same things. I times alpha for the disk is equal to F times D for the disk. And then question is alpha, divide by I, alpha is equal to Ft divided by I. F is given 2 Newton. Distance is what? Of course, radius of the circle, because radius of the disk is the moment arm or lever arm, which is zero point 0.1. 2 times zero point 0.1. And disk is a moment of inertia equation, 1 over 2 m r squared. M is given as 5, r is 0.1 but squared, but put into bracket. So answer will be 8 radian per second. Çok zor bir soru değil ama çok sorulan bir soru Ministry'de. O yüzden bunu kesinlikle öğrenin. And yeah, this is all about the Newton's second law for rotation. Ne dedik o zaman? A force produces a torque, and this torque causes an acceleration. If force is greater, you may get greater torque. Greater torque causes a greater acceleration. If your force is small, it produces small torque. So small torque causes smaller acceleration. Bu şekilde bir zincir. There is a chain between these two equations. And then we will define another physical quantity, which is known as angular momentum. Momentum is defining, in fact, how strong the motion of an object is. You defined the linear momentum in the 11th grade. Now we will define the angular momentum in the 12th grade. So if an object is moving, first I will remind you the 11th grade part just to make a connection between these two. If an object is moving with some linear speed, this object possesses some linear momentum. And linear momentum of an object is determined by mass and speed or velocity. So this train has a momentum because it has a mass, very big mass. It also has a very big speed. In fact, speed is not so big, but momentum is so huge because momentum is proportional to mass and also proportional to speed. Rotational motion, if an object is rotating with some angular speed, this object possesses some angular momentum. Angular momentum symbol is L. An object has a moment of inertia I. Object has an angular speed omega. When we multiply L, I and omega, we will calculate the angular momentum. Yani in linear motion, linear momentum V times M times V, angular momentum is I times omega. Ne yaptık? Instead of M, we put I, instead of V, we put omega. L is the angular momentum. Unit'i ne bunun? Moment of inertia kilogram meter squared. Angular speed is, remember, it was radian per second, but radian is not a unit, it's normal added. So kilogram meter squared per second is the unit of angular momentum. Bunları unutmayın, bakın basit sorular soruyorlar ama o basit sorulardan birisi bu olabilir. So angular momentum's unit is kilogram meter squared divided by second. And a question, 2017 second term ministry exam question. A merry-go-round has a mass of 525 kilograms, so its mass is 525, and radius of this merry-go-round is 2 meters. If it rotates with a constant angular speed of 0.2 radian per second, sorry, radian per second, not squared, so which is omega. What is angular momentum? So angular momentum calculated by times I times omega, but we don't know I. First, you should calculate I, and this equation is given in the ministry exam. 1 over 2 mr squared. 1 over 2 m is 525. R is 2 meter, but square of 2. When you multiply them, you get the moment of inertia of this merry-go-round about symmetry axis. And after that, calculate I and omega. 1050 multiplied by omega angular speed is 0.2, 210 kilogram meter squared per second is the angular momentum of this merry-go-round about symmetry axis. And uh, calculating angular momentum is not so hard. Just you are going to find its moment of inertia. You will use the equation I times omega, and you are going to calculate angular momentum. But this part is much more important than the previous part. Conservation of angular momentum. Conservation means if you keep a physical quantity constant, so it's called conservation. In fact, there are so many conservation laws in physics. Conservation of mechanical energy, we will talk about is conservation of electric charge, conservation of angular momentum, conservation of linear momentum. Physical quantities is conserved if some conditions are provided. If some conditions are provided. Translational motion'da şöyle bir şey var. When the net external force acting on an object is zero, remember this is condition for equilibrium, the linear momentum of an object does not change. So this is known as conservation of linear momentum. But in rotational motion, instead of net force, we have net torque. If the net torque acting on an object is zero, yani if any force cannot produce a torque on an object, angular momentum of that object does not change. This is known as conservation of angular momentum. This sentence is so simple, ama when I ask questions, it become I don't know, somehow difficult. Angular momentum can change only with the torque. If no torque acts on an object, angular momentum of that object cannot change. It stays constant. If it is 10, it stays 10. If it is 20, it stays 20. If it is 0, it stays 0. So no net torque, no change in angular momentum. So, but application of these problems are, I made some connection between the 11 and 12th grade, but 11, I will skip this part, 12th grade part. So what kind of problems we are going to meet? So one example is this merry-go-round. It's a rotating huge disc. A student is on this merry-go-round, so together rotating with the disc. Yani this disc has a moment of inertia, so it has an angular momentum as it is rotating. But this student is following a circular path on together with the um, merry-go-round. This student also has a moment of inertia, also has an angular momentum. So sum of these two angular momentum will give us the initial angular momentum of the system. But as student is walking on this merry-go-round, only moment of inertia of student changes because no external force is acting on this disc. And nobody's pushing this merry-go-round. Nobody's trying to stop merry-go-round. Only what is changing here, distribution of the mass. Why? Initially, student is far, finally walking towards the center close. So only thing which changes here, only thing is moment of inertia. So no torque is applied for that as an angular momentum is conserved here. Initial angular momentum and final angular momentum of this system is constant. As moment of inertia of the system decreases, of course, so its angular momentum increases. Why? To keep angular momentum constant. Because we have equation L is equal to I times omega. L is constant. If I decreases, omega must increase. If I increases, omega must decrease. So remember, maybe we put, this is a good example about how angular momentum is conserved. Ice skater. Why ice? Because ice is almost friction is zero, so no force, so no torque is produced. Net torque is zero, which means condition for conservation of angular momentum. Angular momentum is conserved, but this ice skater for conservation of angular momentum. So if you make the moment of inertia smaller, because angular momentum is conserved, angular speed increases. If you make angular moment of inertia greater, so you are going to decrease the angular speed. So that, which means angular speed and moment of inertia, they are inversely proportional. Why? Because L is kept constant. So this is known as the conservation of angular momentum, total angular momentum of the system before interaction. When I say interaction, like changing the shape of the body, or like walking on the merry-go-round, or sliding on an object. So this is interaction. So before interaction and after interaction, total angular momentums are constant. Yani I initial omega initial is equal to I final omega final. Unutmayın, no torque acts on an object, so angular momentum of that object is constant. It never changes. And I will make just one application about this problem. Yes, this merry-go-round question is the question which I'm going to show you. A 65-kilogram student is spinning on a merry-go-round that has a mass of 525 kilogram. So this merry-go-round has a mass of 525 kilogram, and its radius is 2 meters. It's 2 meter. And a 65 kilogram student, this student is spinning together with the merry-go-round. So then we can say that this system consists of a merry-go-round. Student has two components. Merry-go-round is one component. Student is the second component. She walks from the edge of the merry-go-round towards the center. She starts walking. So initially she was here and then walking here and then coming closer to a point which is closer to axis of rotation. So towards the center, if the angular speed of the merry-go-round initially 0.2, right here it is 0.2. So what is the angular speed when the object reaches to a point which is closer, 0.5 meter from the center? So what is final angular speed? You can easily predict that. So because moment of inertia is decreasing when you are approaching to the center, so angular speed must increase. So you are going to calculate an angular speed greater than 0.20. So it will be 0.24, 22, 24, 25, something like this. You will calculate it. So then equation, total angular momentum of the system before interaction, I initial, omega initial. Total angular momentum of the system after the interaction, I final, omega final. So I initial, omega initial, of course, as I said, there are two components of the system. One of them is merry-go-round, I of merry-go-round. So, and second one is student, I of student. But later, again, two components. Because merry-go-round is a rigid object, its shape is not changing. Same moment of inertia equation you will use, but for student, equation is the same, but radius are different. Initially, student is at a distance of a longer radius, finally at a distance of a shorter radius. For that, as in, I will write for students, I see initial and I student final. Merry-go-round is a disk. Moment of inertia is 1 over 2 mr squared. Merry-go-round is a disk, moment to mr squared. Same number, same equation. Student is following a circular path, so it's a point mass. That's why it's the equation for moment of inertia, mr squared. Mr initial squared, mr final squared. You are going to multiply them, initial angular momentum, angular speed, and final angular speed. The rest you are going to insert the equations. Mass of merry-go-round, 525. Radius of merry-go-round, 2 meters. Mass of student, 65 kilogram, given in the question. Initial radius, initially at the edge, so it is the radius of the merry-go-round, which is 2, square of 2. Initial angular speed is given as 0.2, right here on 0.2. And then final. Merry-go-round has no change in shape, that's why 1 over 2, 525 plus 2 squared again. But student now closer to axis of rotation, what's changing? Radius is 0.5. And calculate final angular speed. The rest you are going to use your calculator and you will get the angular speed as 0.25 as expected, because student is getting closer to the axis of rotation. So moment of inertia of student and so the system decreases. That's why angular speed is increases. Bakın bunlar size directly they are asking the ministry exam question like this. If a student walks towards the center of a merry-go-round, angular speed increases or decreases? So increases. If student moves away from the center, angular speed of the system increases or decreases, it is decreases. Yani bunları bilmeniz lazım. Angular speed and moment of inertia are always inversely proportional. This is all about the conservation of angular moment. Speed of an object undergoing free fall from the same height. Yani buradan